I will invite David Stevens to come and talk to us about RORB that Valerie so enthusiastically endorsed. So we'll all get to know more about that. Please welcome David.
Yes, thanks, Lindsay, and thanks very much, Val, for describing RORB as a Porsche. That's the first time I've heard it described in that way, so really appreciate that. Just by way of introduction, I work for a small consulting firm called Hydrology and Risk Consulting. We are the current custodians of the RORB software. And what I'd like to do today is really just run you through some of the things that we've been doing to RORB over the last couple of years in order to try and make application of ARR2016 really easy and really straightforward. So hopefully, if you take away nothing else from what I'm saying today, hopefully it's just an impression that if you wanted to pick up RORB and use it to do an ensemble or a Monte Carlo type simulation, it's actually really easy to do, and it doesn't take a lot of effort to do that. So firstly, just a little bit of background. What is RORB? RORB is a event-based rainfall runoff model that's been used to do design flood estimation in Victoria and interstate and overseas for a number of years. It was first developed by Eric Lawrenson and Russell Mine at Monash University back in the late 70s, and it's been progressively upgraded and enhanced over time since then. A lot of the principles in RORB are really the conceptual forebears to a number of other modelling packages that are widely used around Australia as well. So there's a really long pedigree of application of RORB to a bunch of different catchments, both rural and urban, right around the country. RORB's really stayed popular for a whole bunch of reasons. One of the key ones is simplicity. There's only 4 parameters in RORB that you need to adjust, and one of those we typically leave at the default value the whole time. So you've really only got 3 parameters that you need to fit to any given application. Because it's been around for so long, as I said, it's been applied in a lot of catchments right across the urban areas of Melbourne, urban areas interstate, but rural areas as well. And so there's a really good database out there of people who have applied RORB to different situations, calibrated it to gauge data, and come up with estimates or relationships that describe how the RORB parameter values tend to behave in different circumstances. So that provides a really useful data set to when you're applying RORB in an ungauged catchment. RORB has been continually developed, and I'll talk a little bit about that today. We're still actively developing it with Melbourne Water to keep it up to date and to keep it efficient and user-friendly. And it is Melbourne Water's preferred hydrologic model. So Melbourne Water have been very generous in their ongoing support for RORB over a long period of time. And one of the things that they've really enabled to continue is RORB is provided free of charge to industry. So you can download it off our website for free. All we ask for is your email address so that if we find a bug, we can send you an update. But there is no charge involved in getting your hands on RORB. There's also a whole bunch of GIS plugins that are associated with RORB these days for map info and also for ARC-RORB that really make the process of developing RORB models a lot more efficient than it perhaps used to be a number of years ago. Probably the other thing I'll say that isn't up there is that one of the reasons RORB has also stayed popular is it's really, really flexible. RORB's really scalable to very small catchments and very large catchments, and it also includes a number of features that allow us to model all the different sorts of hydraulic controls that we see within urban catchments, like retarding basins, like pit and pipe type systems. All of that stuff can be simulated within RORB. It's quite possible to do that. So I wanted to spend a little bit of time now before I get into the detail of how to do this in RORB and just think a little bit about the nature of the problem that, to a degree, ARR2016 is trying to address. What I've got here is a series of results that we've derived for a catchment. This is not an urban catchment, and it's quite a large catchment, but the principles that I'm going to describe here are common regardless of where you are. What we've done here, we've got, that doesn't work. We've got AEP on the x-axis and flood magnitude, peak flow on the y-axis here. And each of these dots represent a hydrologic model run that's been done for this catchment. What we've done is taken a design rainfall frequency curve, so just the IFD data from the Bureau of Meteorology website. We've fed that into a RORB model, and then we've run it thousands of times. And every time we've used a different IFD value, and we've used a different rainfall temporal pattern, a different loss rate, a different spatial pattern. What we've been trying to do here is explore the sensitivity of the results to how the rainfall manifests itself in space and time, and what condition the catchment is in when the rainfall hits. Is the catchment wet? Is the catchment dry? What you can see here is you get an enormous scatter of results. If you look, say, at the 1 in 100 AEP, turns out if you put a 1 in 100 rainfall on this catchment and you vary other stuff like the temporal pattern, like the spatial pattern, like the losses, you can end up with a peak flow that ranges anywhere between 400 cumex and 2,000 cumex. So it's just an enormous range of variability that's attributable from all those different factors like spatial pattern, like temporal pattern, like losses. Similarly, you can flip that round the other way and say, well, what if I've got some kind of flow threshold of about 1,000 cumex? That's a level beyond which houses start getting flooded or something similar. If you look at it in this way, you can say, well, I can get 1,000 cumex flood from any rainfall in between a 20% or a 1 in 5 and a 0.1% or a 1 in 1,000. Depending on the catchment conditions and the temporal pattern, the spatial pattern, I can put any of those rainfalls on and actually hit that threshold that I'm interested in. What this demonstrates to me is that there is an enormous amount of variability that we need to try and be accounting for when we're thinking about design flood estimation and hydrologic design. And really ARR2016 has tried to kind of, I suppose, simplify or average out a lot of that variability in quite a straightforward manner. ARR2016 is encouraging us to look at this range of variability and try and account for that when we're doing our hydrologic design. Val showed this slide before. So what we had as part of, or what we've been doing for a very long time here is the method on the left-hand side, the simple design event, where we've taken a RORB model, say we've put in a single temporal pattern, a single IFD, a single rainfall depth, and a single value of our initial loss, say. We've run that through our model and we've come up with a single hydrograph. And we've said, well, great, that's the answer we're going to use. What ARR2016 is suggesting is, rather than doing that approach, let's think a little bit more about the natural variability that we're generating from things like rainfall temporal pattern and our catchment wetness, our losses. So we've now got ensemble approaches where we're saying, well, let's take, rather than using a single temporal pattern, let's take a set of 10 temporal patterns and run our model 10 times and then look at the variability in the outputs and pick a median. Similarly, you can also do Monte Carlo, where we're looking perhaps at the joint probabilities of temporal pattern variability and loss variability and kind of sampling all those different forcing factors in a sort of statistical way. We won't talk too much about that today. But really, for what ARR2016 is now saying is you can no longer do the simple approach. You've got to think in some way about the variability that you're experiencing in these kind of natural inputs. So it's no longer enough to take a single temporal pattern and say, this is our temporal pattern that we're going to use. We've got to think a little bit about the variability. So I guess where that all comes back to is where do we go from here? And we've tried to think really hard about this in RORB and tried to really carefully develop RORB to make the application of ensemble and Monte Carlo approaches really straightforward and really easy to do. What the latest version of RORB does now is it will read the rainfall IFD data that you download from the Bureau of Meteorology website and the other design inputs like temporal patterns that you can download from the data hub. It will read those text files straight in for you and provide a really straightforward way to kind of run all those different combinations and look at the outputs. And I think I'd certainly concur with Val and Michael that ensembles, although you're running the model 10 times, it doesn't need to be 10 times the work. We've tried really hard to sort of automate a lot of that process and make the results really quite easy to use in subsequent modelling steps like HEC-RAS or 2Flow or whatever it happens to be. So I will now spend a little bit of time talking about those data sources and how you access them and how you get them into RORB. And wanted to start first of all talking about the IFD data, the design rainfall frequency data. This is, I suspect most people have used it, but it's still available from the Bureau of Meteorology website. You can download it as a CSV file and read that CSV file directly into RORB. The CSV file obviously is also editable in Excel, and if you're looking at design rainfall depths rarer than 1%, you sometimes have to download a couple of files from the Bureau and sort of merge them together before you use them in RORB. But if all you're interested in is up to the 1%, then you can just download a single file, read that in and off you go. This is what the web page looks like in the Bureau. I'm sure most people have seen this. There's a little button up in the top right hand side where you can just download that data as a CSV. As I said before, the Bureau have decided to provide this information in a range of different kind of bins. So the default you get is on the left-hand side there, IFDs, frequent and infrequent, which goes all the way from, I think, 1 in 2 or 63% up to 1 in 100 or 1%. You can also get the very frequent data, so the sort of 1 to 12 EY information. And you can also get at the minute rare design rainfalls for long durations. So this is 1 in 200 up to 1 in 2000. Unfortunately, if you want that information, you've got to hit that radio button and it brings up another table, which you then have to download separately. You can read all that information into RORB, but you've got to sort of open it up in Excel and kind of copy and paste the data together. My understanding is the Bureau are thinking about changing this so that you can download kind of the entire rainfall frequency curve in one file, but I'm not sure what the timing on that is. So that's IFD data. The next one is the R&R Data Hub, and again, Val and Michael have mentioned this. What we can get from the R&R Data Hub is a whole series of other information that's useful for our design flood estimation, including aerial reduction factors. So if you're working in larger catchments, I think sort of 75 square K and up, you'll need to convert your point rainfall depths that you get from here, from the Bureau, into a catchment aerial estimate. You also get the temporal patterns, so I'll talk a little bit about what they look like and how you get them. And you can also get regional estimates of pervious area losses, which can be helpful as well. The Data Hub also provides us with estimates of pre-burst rainfalls. Now, I won't spend too much time talking about this. RORB actually doesn't use them at the minute, but we're currently working on an upgrade with Melbourne Water that will allow that pre-burst information to be read in and used automatically as well. Similarly to the Bureau data, the Data Hub file can be downloaded as a text file, and for the temporal patterns as a CSV file, and then those two files can be read directly into RORB so that you can just pick up that information and use it straight away. This is going to be really hard to see, but this is an example of the kind of results page you get from the Data Hub. And really should acknowledge here that the great work of Mark Babister and his team from WMA Water, who have set up all this this interface. It's really quite a useful one. What you get, again, that's probably hard to see, but if you put in your catchment into the Data Hub and click Submit, you get all this data, and then you get a little download button at the bottom of the web page. So what you can do is click on that, and it downloads all that information for you in a text file format. That can just be then read straight into RORB. Similarly, you can also get your temporal patterns. So there's another little download button there that actually gets your 10 sets of 10 temporal patterns. It gives you that in a CSV file format. And again, that can be read directly into RORB. It's really pretty straightforward and efficient. One thing I will note is that there are actually different sets of temporal patterns, and it depends a little bit on what kind of modelling you're doing. If you're looking at very small catchments, so I think the guideline is less than 75 square K, there are point temporal patterns, point rainfall temporal patterns. If you're looking at larger catchments, larger than 75 square K, there are what they call aerial temporal patterns. And there's differences in the way that those sets of temporal patterns have been derived from the recorded rainfall data. But really, from a practitioner's point of view, all you really need to know is, am I working in a catchment that's smaller or larger than that kind of key threshold of 75 square K? And that then tells you which sets of patterns that you'd use. This is what the temporal patterns look like, and so I've got a plot here on the bottom right hand side that shows you a set of 10 temporal patterns that have been downloaded for a location from the Data Hub. And what we're showing here is time on the x-axis, so these are 6-hour storm patterns, and then total rainfall depth on the y-axis, and that's measured in percent. So you can see after 6 hours, all of those 10 temporal patterns have reached 100%, but through the course of the event, they vary quite considerably as to how much of the total percentage has been delivered at various points in time. So there are a number there that are quite what we call front-loaded. There's an orange one sort of at the top there. If you look, we're a couple of hours into the event and already 60% of the total rainfall depth has happened. So that particular pattern is very, very front-loaded. There's others that are very, very back-loaded, whereby you get to sort of 4 hours through and you've only had 40% of the rainfall depth. And this sort of variability, it drives a lot of the differentiation in peak flow that you see when you start to sample these different temporal patterns. With the same IFD depth and the same losses, you'll get quite different results if you just vary your temporal pattern. So really important that we're grabbing this data and seeing how it affects our design flood estimates. To complicate things a little bit, the data hub gives us different sets of temporal patterns depending on what our AEP of interest is. So I've got a little plot up the top there that's been taken straight from ARR2016, and there's sort of 3 or 4 different bins on that plot that describe the AEPs that sit within those bins. So we've got frequent, which gets us up to about 20%, intermediate, which takes us up to about 2%, and then rare, which takes us up to about 1%, and then very rare beyond that. So when you download temporal patterns from the data hub, what you'll actually get is 10 sets of temporal patterns in each one of those bins. So there's 10 temporal patterns that are valid for the frequent events, 10 that are valid for the intermediate, and 10 that are valid for the rare. The very rare I don't think are there yet. I'm pretty sure they're still being worked on. So you actually end up with 30 temporal patterns, and you then got to think about, well, what's my AEP of interest? So which set of 10 am I actually looking at? And again, the nice thing that we've done or tried to do in RORB is sort of automatically account for all this. So if you're running RORB, what it'll do is it'll say, what AEP am I running at the minute? So which bin am I in? Which set of 10 temporal patterns do I need to look at? And as I said before, of course, there's also the issue that you've got the aerial temporal patterns. So they're for catchments larger than 75 square K, and they're a different set again. So there's a little bit of complexity you need to be aware of, but we've tried really hard to sort of make that quite straightforward and efficient for users. This will be really hard to see as well, but this is basically our design rainfall dialog box in our latest version of RORB. So I just wanted to very quickly step through this and show you where all of these different inputs are. Basically, once you've set up your RORB model, you've set up what we call a catchment file, which basically describes the physical properties of your catchment. You can then start running the model, and this is the main screen where you're entering most of that design information from ARR 2016. First thing you do is at the top there, you just give it a link to the text file that you've downloaded from the data hub. So that's sitting on your drive somewhere, so you just click browse and link directly to that. And it reads in all of that information that's been populated from the data hub, including the error reduction factors, the regional losses and other bits and pieces. You've got a separate file for your temporal patterns. So again, you've downloaded that from the data hub. That's a CSV file. You just link it straight into RORB there, and RORB reads it all, does all the hard work for you. And you've then got a third file, which is your IFD data that you've downloaded from the Bureau website. And again, that's a CSV format. You just link it straight in and RORB reads it all for you. All you need to do then is just tell RORB the simulation type you want to do. So RORB can still do a simple design event, so one temporal pattern, but it can also now do ensembles, and it can also do Monte Carlo. What I've chosen here is an ensemble simulation, and I'm actually doing a batch ensemble simulation. So I'm looking at durations ranging from 12 hours to 168 hours, and AEPs ranging from 10% up to 1%. And in each one of those different AEPs and durations, I'm running the model 10 times with 10 different temporal patterns. So there's hundreds of runs that are being done here, but it's all that work's being done in the background for you. So you don't need to sit there and vary the inputs or anything like that. All of those inputs are being read for you from the input data files, and RORB is just picking them up automatically and doing all the runs, processing it all for you. And it's quite a quick process to do. You can run something like this in less than a minute, I think. So that literally is all you need to do. Have a very quick look at the outputs. The outputs are presented as a plot, but also as a text file, and this is an example of the text file output. What we've got here is we're just showing a summary of the peak flow at the downstream outlet of this catchment for each of the individual model runs that we've done. So I've outlined here a block of 10 model runs, and they are basically the 12-hour, 10% AEP ensemble simulations. So there's 10 runs in here. They're all 12 hours duration. They're all 10% AEP. So same rainfall depth has been put on all these model runs. The same losses have been used for all these model runs. The same KC routing parameter values have been used for all these model runs. The only thing that's been varied from run to run is the temporal pattern. And so there's 10 patterns that are given to us by the data hub, so it's been run 10 times. That's just simply the results of an ensemble simulation. What you can see there of interest is that the lowest value that's been produced is 18 QMEX. The highest value that's been produced is 70 QMEX. So again, there's an enormous variability that's being driven in those peak flow results simply from temporal pattern alone. Nothing else has changed in these 10 simulations. So you can sort of look at that and say, well, that's great, but I ultimately need to provide a peak flow to be used in design, hydrologic design, or I need to take a single hydrograph through to a HECRAS model or a two-flow model or something like that. RORB, again, gives you the ability to pick out from an ensemble result the numbers that you should be carrying forward into subsequent design. So you can look at these and do a really simple calculation on just the median. So the median of those 10 numbers is 46.7 QMEX. Then I can say, well, why don't I just take the run that's immediately larger than the median? And in this case, it happens to be temporal pattern number 1. Peak flow is 48.5 QMEX. So that's the run that's nearest to, but just slightly larger than the median of those 10 numbers. And that is our best estimate of the 10% 12-hour flow. RORB gives you this in a summary file that you can use to calculate, like Val and Michael were showing before, the box and whisker type plots. But it also gives you the complete hydrographs that underlie each one of these model runs. So having said, well, I'm interested in temporal pattern number 1 for the 12-hour duration 10% AEP, I can go to the directory where that was run and immediately find all of the text files, all of the full hydrographs for each one of those runs, and pick them up and use them as boundary conditions to my two-flow model. I can use them to do design of a retarding basin. I can use them for whatever I want. The important thing is I've recognised and I've accounted for the variability that temporal pattern has driven in my results, I suppose. And it's been done in a really, really simple, straightforward manner, really easy to do. Didn't take much longer than a simple design event. So I think I've said all that, everything on that slide. The results are provided in RORB as a series of both individual runs and a batch summary. You can use box plots if you want to show some of that variability across the different durations and also within durations. But importantly, you can really easily pick out the individual run that's associated with the median that you want. So it's not hard to go from that kind of analysis to getting full sets of hydrographs, and you can have hundreds of hydrographs if you're doing a complicated two-flow model, or you can just have one if all you need is one. Just to wrap up, I wanted to very quickly mention where RORB's heading in the next few months to years. So Melbourne Water are currently going through a process where they're revising their technical specifications for flood modelling. And in parallel to that, we've been working with them to also undertake some enhancements to RORB that will help make it more ARR compliant. So it will use more of that information that's being provided by the data hub, and it will also hopefully make it even easier to do ensembles and Monte Carlos. So some of the things that we're looking at introducing is to have a specific distinction between the losses that are applied to directly connected versus indirectly connected impervious areas. So that's something that's been recognised in RORB 2016. We're also going to include the pre-burst rainfall, as I mentioned before. And we're also going to look at what's called embedded burst filtering of temporal patterns. Now, embedded burst filtering of temporal patterns will help address that issue. I think it was raised by a question before, where in your sets of 10 temporal patterns, you sometimes see some that look really, really extreme. They don't sort of fit in with that how you'd expect a rainfall temporal pattern to look. So embedded burst filtering will help pick up those kind of outliers, and will kind of filter them back or filter some of those irregularities out of them. We're also going to make this process here, where you go from your summary results to a particular hydrograph, even more efficient to grab out that one hydrograph that you need. So hopefully it will make ensembles and Monte Carlo as well even easier to do. So that was me. Thank you very much for that, and very happy to take a question or two.
Thanks, David. We've got a couple of minutes for questions from David, so if anybody wants to make Chris run, put your hand up. Mick, I think you're first off the rank.
Hey, David. Just a quick question. Oh, Mick Turnley from ACOM. Just a quick question. There's probably a bit of variation in terms of how people are selecting median out of 10 temporal patterns across industry. What is your take on that at this point in time?
Yeah, you're right. There is a bit of variability, and you do see different approaches. Some do medians, some do averages, and other bits and pieces. That what I've just outlined there is typically the way we tend to do it. But to my knowledge, there is no hard and fast guidance on that yet. So I think that's something that we're waiting to see. Hopefully, as I don't know, as a bit of an extension to ARR2016 probably, because it